Aggregates serve boundaries between logical groupings within our application. We enforce these boundaries by prohibiting direct references to objects within an aggregate that aren't the root of the aggregate. Consider the customer with the address. It's perfectly okay for customer to reference address. Address might be an entity or it might be a value object. It doesn't really matter in this scenario. What's important, though, is that the only way to get to the address in this aggregate is through the customer. We won't be referencing an address by some identity outside of this aggregate. But that's not the case for customer. Since the customer is the aggregate root, it can be referenced from other aggregates.
In this common example, an order might reference a customer. Depending on our context, it might make sense for a customer to reference an order. In this case, let's assume it only makes sense for the order to be central to the application's design. What's not okay is for the order to reference a customer's address directly. This violates the integrity of the customer aggregate.
Remember that aggregates and aggregate roots only apply to objects, not data. And when we're talking about references, we're talking about object references, properties that use an object directly. This is especially important with ORMs. For example, if you were to save an address that had a customer object attached to the customer property, there are scenarios in which Entity Framework would involve the customer in the database insert or update, possibly even a delete. And this behavior leads to a lot of confusion. I frequently advise developers to just remove the navigation property and use the foreign key ID instead. It's a little more work, but removing some of the ORM magic results in more control over the behavior. And this aligns perfectly with the fact that one common way to enforce aggregates is to replace direct navigation properties in the model's non-root types with key references, and this reduces the number of dependency relationships within the model. Since we're dealing with appointment scheduling, our initial design might look something like this. An appointment involves bringing together a patient and a doctor in an exam room for a particular type of exam. And since we'll typically need to know the owner's information when we deal with the scheduling, it's important to have a reference to the client from the patient also. So if we model our system this way, anytime we saved an appointment, it's going to scan all of these objects for changes and save them as well. So modeling it this way, the scope of our domain for appointment scheduling is much greater than it needs to be, since in our case, we don't expect to modify any of the other objects when we're creating an appointment.
Right, an appointment is basically just a list of resources tied to a particular time span. It models who, what, when, and where, but it doesn't ever need to change any of these associated concepts. As a result, we can simplify our design by eliminating most of these object relationships from the appointment class's design. Recall that for an object to be a good candidate for being an aggregate root, it should be the case that deleting that object should also delete the other objects within the aggregate. In the design shown here, if a customer cancels an appointment and we delete it from the system, it doesn't make sense that this should delete all of the associated objects.
So here's another perspective on that same model. By simply including the IDs of the related concepts rather than object references, we're able to ensure that creating and changing appointments has a minimal impact on our system when we persist the appointment. This relationship works because an appointment in the real world is really just a note that includes a place, time, and additional details. Adding and removing appointments shouldn't impact the people and places involved, and this revised design reflects this.
We do still have a bit more learning to do with this model, though. Somewhere in our design, we need to enforce certain invariants about appointments, like that they shouldn't be double booked. Our current thinking is that appointments need to include this rich behavior with regard to how they're scheduled. It's the aggregate root's responsibility to verify any invariants the aggregate may have, and in this case, the appointment is still acting as an aggregate root, even if we've eliminated the navigation properties to the other objects that it might be working with. Let's make sure we're clear on invariants, and then we'll see how invariants in our application impact our design. An example of an invariant in the real world is the speed of light, which is a constant that you just can't break in terms of the physics of the universe as we know it. Some things in your system must be true in order for the model to be consistent or valid. Other examples of invariants might be that the total of the items on a purchase order do not exceed the PO amount, or that appointments do not overlap, or that an end date on an object must follow the begin date on that object. Sometimes an invariant only involves a single object. Maybe a particular property or field, such as name, is required. In this case, we may model the system such that one can't even create the object without the required information. Our value objects are like this. For example, you can't create an instance of a date-time range object without defining both the start and end time. However, sometimes the invariants involve how multiple objects relate to one another.
In the example here, the purchase order and the individual line items would most likely be modeled as separate objects. However, the purchase order would be the aggregate root, and as such, it would be responsible for verifying this invariant. The individual line items on the purchase order probably don't know anything about one another, nor should they. So it wouldn't make sense to put the responsibility for enforcing this invariant in the line item object. What about appointments? How does one appointment know whether it overlaps another?
As we focused on these invariants and where they belong in our design, it became clear to us that the appointment didn't really make sense as an aggregate root. If you apply this thinking to our appointment scheduling context, it follows that one appointment doesn't really know anything about other appointments, but the schedule knows about such things. Let's evolve our domain model to follow this pattern and see where that leads us.
This feels like a big change to the model. And these kind of epiphanies happen when you're working on the model. But that's not a bad thing. It's not like you've wasted a lot of time focusing on appointment as an aggregate root. This is the beauty of modeling your domain, having conversations with different people, with the domain experts, because ideas like this bubble up and suddenly something big like this becomes clear. So you're not going to get it 100% right the first time. Your understanding will evolve as you learn more about the domain. And from time to time, you'll realize there are big changes that can dramatically improve your design. In the domain-driven design book, Eric Evans talks about these breakthroughs in his section about refactoring toward deeper insight. This is really an important part of domain-driven design, and about a quarter of the book is dedicated to it. Let's take a look at the signs that Steve and I eventually recognized in our domain, which led us to shift our appointment aggregate to a schedule aggregate.
Originally, our solution had the appointment as the central focus of the design. I had figured it would be its own aggregate, with appointment at the root and its various properties as its children. As we've just discussed, that doesn't really work as well as I'd hoped, so now we're refactoring the design to introduce a new type, the schedule. Before we show that though, let's review the original structure and some of the reasons it didn't work as well as an aggregate in our solution.
You can see the original structure had appointment in its own folder and marked with the I aggregate root interface, which is required for it to be accessible from our repository methods. It has essentially the same properties as the later version, except for schedule ID, since there's no schedule type yet. And it has the same basic set of methods for modifying its room, doctor, time, and other properties. None of that really changed, since all of those operations only had to deal with a single appointment instance.
However, when the appointment tried to enforce the invariant that appointments whose times overlap for the same pet should be marked as potentially conflicting, things were a bit messier. You see, this appointment doesn't actually have any association with any other appointments, so the only way to enforce this is to use a repository to get those other appointments for the same date as this one. Since entities don't support dependency injection through their constructor, this means an instance of the repository needs to be passed into this method. Creating this repository instance was the responsibility of the calling code, which may not otherwise have needed it. Note also that because the repository's interface is async, this method must now be async as well, even though no other methods on the appointment entity are async.
The real problem here, from a DDD perspective, is that cross-aggregate invariance should not be enforced by any one aggregate. In the case of something like a unique constraint between all aggregates, you might need to use a domain service or another approach. However, in other cases, the need to do this may indicate that you've missed an important part of your model.
Right, in this case, the whole thing that the user is interacting with is the clinic schedule, but nothing in our original model referred to the schedule itself. Since some of our business rules, like what to do with appointments that conflict, only make sense at this higher level, it made sense to introduce a change to our model, the schedule aggregate.
So even though the initial design we had was about scheduling, the schedule itself was never part of our model. Once we include schedule as its own explicit object in our model, it makes the design much simpler. Appointments no longer need to know anything about other appointments. The responsibility for ensuring that appointments are not double booked, and similar invariants, can be performed by the schedule, which is the aggregate root.
So let's see if this passes our other tests about defining aggregate roots. A schedule will certainly help us ensure that appointments don't overlap one another. When we save changes to a schedule, does it make sense to update any changed appointments? Yes, it does make sense. And if we were to delete an entire schedule, would it make sense to delete all of its appointments? Yeah, I think that would make sense also.
Yeah, I think this is the schedule for a particular clinic. At the moment, we only have one clinic, but if we imagine a scenario in which multiple clinics each have their own schedule, it wouldn't make sense to delete a clinic's schedule, but then keep its appointments floating around. So I think that works.
Great. And if a schedule exists for each clinic, then it makes sense to persist the schedule, which means that it needs an ID and therefore is truly an entity. And when we retrieve a schedule, we'll most likely be filtering which related appointments we want to look at. For example, today's schedule or this week's schedule. That would mean we want all of today's or all of this week's appointments from a particular clinic's schedule. It really does make a lot more sense to me to tie the appointments to a schedule than directly to a clinic. Now, let's see how this affects our design. Now we'll show you the new schedule aggregate implementation in our application. In the refactored solution, we've renamed the folder so that now it's schedule aggregate. This folder only includes schedule and appointment, as well as related guards and specifications. In larger applications, it can help to organize your domain model by grouping everything related to a particular aggregate in its folder. Looking at the schedule aggregates code, you can see that it inherits from our common base entity type and uses a GUID for its ID key, just like appointment. This lets us set the key ourselves, rather than relying on a database to do it for us. The class is also marked as an aggregate root with an interface. In the next module, you'll see how we use that to protect the integrity of our aggregates.
Right, we'll see how that works when we look at our repository and specification implementations.
Next, the schedules constructor just takes in its ID, its date range, and its associated clinic ID. In our sample, the clinic ID is always hard-coded, but in a real application, there might be several clinics using the same software, and they would each have their own IDs. The constructor is responsible for ensuring that the incoming values are valid, so that it's always created in a consistent state. Schedule has just a few properties. There's the clinic ID, the associated set of appointments, and the date range. We're careful to only expose a read-only IEnumerable of appointments because our aggregate must encapsulate its internal state. We don't want other parts of our application to add or delete appointments without going through the schedule's explicit methods designed for this purpose. Also, the date range isn't persisted, since it can vary with any given instantiation of the schedule.
Yeah, and for performance reasons, you wouldn't really want to load the schedule aggregate with every appointment that had ever been made included in it. By using a property like this, we make it clear to the rest of the domain what set of dates this instance of the aggregate holds. The actual population of the appointments that match this range is left as a responsibility of the specification and repository classes that are used to retrieve the schedule from the database.
Yes, and the configuration of the aggregate's persistent details is done in the infrastructure project's data config folder. This is where every entity's EF core specific mappings and configuration is performed, which keeps these details out of our domain model. You can see here that we're also letting EF core know that we don't want the database to supply an ID when we create a new schedule. We've marked that property as value generated never.
Getting back to the schedule, let's have a look at its methods. The first method is for adding new appointments. Our design forces all new appointments to come through this method, so we don't have to have duplicate behavior anywhere else in the application to take care of whatever should happen when a new appointment is added. It's all right here in one place, easy to understand and easy to test. The method validates the input to ensure we're not adding bad data to our aggregate, and then it adds the appointment. When a new appointment is added, the schedule is responsible for marking any appointments that might be conflicting. It's the right place for this behavior to live, since the schedule knows about all the appointments and knows anytime appointments are added or removed. After marking any conflicts, an appointment scheduled event is added to the aggregates event collection. We'll see how this works in the module on domain events.
The delete appointment method is similar. After deleting an appointment, the schedule needs to once more mark any appointments that might be conflicting. There's also a to-do comment here. These are left as exercises for you to learn more about how to work with the patterns introduced in this course. You'll find a number of to-do exercises scattered throughout the sample.
We hope you'll take some time to download the code, run it locally, and try implementing some of the to-do tasks using the existing functionality as a guide. There are a couple more in the mark conflicting appointments method, which, remember, was originally on the appointment type when we started out with that as its own aggregate. This method is responsible for detecting and marking appointments that might conflict. The basic rules shown here just checks whether the patient has two appointments that overlap. If any such appointments are found, they are updated to set their conflicting property to true. Then, the current appointments property is set based on whether there are any other appointments that conflict with it.
This is an important This is an important part of the business logic for this application, and it's encapsulated right in our schedule aggregate. In a lot of data-driven applications, this kind of logic might be in a stored procedure, or perhaps just implemented in the user interface. But in a domain-driven application, we want these rules to be explicit and defined in our domain model.
The last method on schedule provides a hook for its appointments to use to notify it when changes are made to one of them. Because we don't have navigation properties from appointment back to schedule, we can't directly call methods on the aggregate root from appointment methods. There are a few different patterns you can use to accomplish this task. For this sample, we chose this one because it's simple and easy to follow. This handler simply calls mark conflicting appointments, but it's exposed as its own separate method because it could do other things as well, and we don't want to expose the internal behavior of the schedule to the rest of the app. To see how it's used, let's look at the appointment class's update start time method. When the application needs to update the start time for an appointment, it will call this method. Because appointment is part of a scheduling aggregate, we know the app will already have loaded the schedule before calling this method. So the second parameter in the method asks for the handler on the schedule that will be called. The call to update the schedule is made after updating the time range property on the appointment. So when mark conflicting appointments is called, it will use the new value for the time range. There are a lot of other ways you can set up this communication, using C# events, static domain events, or some kind of double dispatch approach. They all have trade-offs, and when you need to do this in your apps, you should choose the one that works best for your app and your team.
Let's see the final result in the application. This change to our model of adding in a schedule aggregate made a big difference to how the domain model is organized. It gave us a much better place to put the logic of enforcing business rules around combinations of appointments and business logic that needs to run when appointments are added or removed.
Right, without the schedule, we would have had to use a domain service or something to add behavior around the newly added or removed appointments. But with this design, we can go into the schedule, add a new appointment for Rosie, and then add another one, and you can see the notifications being triggered by the events, as well as the red outline representing the conflict in these two appointments. Not only is our domain model clean and easy to test, but even more important, it actually works.
And notice that as we move one of those conflicting appointments to another spot, the red alerts disappear. Good job, Steve. I am so grateful that you let me off the hook for working on the front end of this application. You know I'm more of a back-end developer. So let's step back a moment and review some of the things we've just learned about designing aggregates. First of all, aggregates exist to reduce complexity. You might not always need an aggregate. Don't add complexity just for the sake of using an aggregate. Another is that entities with an aggregate can only reference the root entity of another aggregate.
But you can always use foreign key values as a reference to entities inside another aggregate. It's perfectly okay to use this, and it'll avoid the need for, when you go to save that aggregate, for it to cascade its persistence into other aggregates. If you find you're needing to use a lot of foreign key references to aggregate children often, you may need to reconsider the design of your aggregate in your domain model.
Another pointer was don't be afraid to have an aggregate of one. In other words, an aggregate that only has one object in it.
And finally, don't forget the rule of cascading deletes. Remember, one test for whether or not a particular object makes sense as an aggregate root is to consider whether deleting that object should also delete all of the other child objects in that object's hierarchy. If it doesn't, then you have probably chosen the wrong structure for your aggregate.
Once again, we have covered quite a bit in this module. Let's review some of the terms that you learned in this video. The first thing we talked about was an aggregate. An aggregate is a group of related objects that work together in a transaction. The root becomes the entry point through which you do any work with the aggregate, and the root also is what's in charge of making sure that all of the rules that apply to that graph of objects are met.
Each of the rules that describes the state that the system must be in order to be valid is called an invariant.
Within our aggregates, we have objects that are related to one another. In DDD, we refer to these relationships as associations. If you use an ORM, you may hear the term navigation properties, which refers to those properties that reference the related objects in the model. And we talked about the importance of defaulting to one-way relationships, which we also refer to as unidirectional relationships.
In addition to these important terms, Steve and I shared a lot of guidance around creating aggregates and roots in your domain models. Nobody wants to work with a big ball of mud. We use aggregates to organize our model. An aggregate is a set of related objects that live in a single transaction while encapsulating the rules and enforcing invariance of that transaction, making sure that the system is in a consistent state. When designing how related objects work together, your job will be easier with one-way relationships. Use those as a default and only introduce bidirectional navigation if you really need to.
And most importantly, don't resist updating your model as you and your team of domain experts learn more about the domain. Hopefully, most of this will happen early on, and then just once in a while, you might have a big breakthrough, like we did when we realized that the schedule made more sense as an aggregate root than trying to have each appointment be its own aggregate. Up next, you'll learn about repositories, which are a critical pattern in domain-driven design.
This is Steve Smith.
And I'm Julie Lerman. Thanks for watching Domain Driven Design Fundamentals.